friends, welcome back to my channel. We're officially on week 4 of the System Design Interview Prep series. But before I get into the most exciting world of databases, this week I hit 1,000 subscribers, which I'm super excited about. And if you're new here, my name is Gigi. I'm a senior software engineer. I've been working in big tech for about 5 years now. And the reason why I started this channel is to create a safe space for learning and give a little bit of a different perspective on the tech world. Hopefully something that's a little bit more down to earth and a little bit less anxiety ridden, because the job market, it effing sucks. Like, we all know that it sucks. A lot of people I see on here are like superstar FAANG engineers that are deep diving into technical topics, but I want others to remember that being a good engineer is a skill. Like anything, it can be learned, and it doesn't have to be something super intimidating. So I drop a new tech video every week, but if you take a look at my shorts, I also talk about fitness and finance, which are my other interests/passions, and I'm gonna start posting other videos on my main channel too about these things. But in the meantime, enjoy the Technical Talk series. And please give a like and follow and comment if you like these videos. And let's just go into today's lesson. Okay guys, so this week we're gonna be talking about database partitioning. Another week of databases. Yes, I know. I'm a little bit tired of talking about it too, but these are gonna be the last 2 weeks of this part of the series and we're gonna be moving on. But nonetheless, this is actually very important. So last week we talked about database replication and how it helps with things like fault tolerance, performance, reducing latency, and also scalability. But what happens when you have so many writes that a single server can't take it? Or what happens when our data set becomes too large that a single machine can't hold all of it? This is where something called database partitioning comes into play. So database partitioning is the act of splitting up our big data set so that different servers handle different portions of the load. So we can compare the concept of database replication and database partitioning to the concept of a library. So think of all the books in a library as one big data set. When we have multiple copies of a single book, we can compare that to database replication. Now think of when we have multiple different categories of books. We have science fiction, we have nonfiction. I don't know what other categories there are, but you get the idea. So when a user wants to go look for a science fiction book, they don't have to sift through the whole library in order to find that type of book. They can just go to the specific section and it makes their search a lot more efficient. And that's kind of what we're doing with database partitioning. A database can be made up of one or more physical servers. Database partitioning takes this data and splits different parts of the data onto different servers. So there's 2 major reasons I want you guys to remember of why we need database partitioning. The first reason is to improve the efficiency of our read queries. So if we have our data partitioned into smaller sections, the amount of data that we have to sift through in order to find the data that we're looking for is a lot smaller, and it makes our read queries faster. So every time a database handles a request, whether it be a read or a write, it uses a certain amount of CPU and memory. So if we're able to split these requests between multiple nodes, we can keep the CPU usage for each node within a reasonable threshold. So when you're going to choose a database partitioning strategy, the strategy that you end up choosing will highly depend on how you access your data. You want to make sure that the requests are distributed evenly amongst the nodes. And we want to avoid things called hotspots. Hotspots are when a certain node or group of nodes receive a high number of requests. When this happens, this defeats the purpose of all the things we're trying to optimize for. It makes our reads queries slower because we have more data to sift through, and it's also more resource intensive when that node is going to handle requests, because all the requests are going to that node. So let's get into our first type of database partitioning called range partitioning. In range partitioning, we have a contiguous set of keys ordered in some fashion, and we assign a subset of these keys to each database node. So in this example that I have here, you can see that we have the key being the timestamp. We assign a certain set of months to each node. Within each node, as I said, the keys are ordered, and we can use an index to keep these keys in an ordered fashion. So if you think back to episode 2, when I talked about database indexes, SS tables and B trees will help us here. So there are a few pros to this approach. One, the data is ordered, so it's good for range queries. And secondly, it's easy to add or remove a partition because the data is ordered in a certain fashion, so it doesn't affect the data around it. So if you want to create a new partition, you just create a new table with a specified range and add it to the set. Now the cons here depend on your access pattern. Here we have a higher likelihood of hotspots. If we're using something like timestamp to partition, and say we're only accessing the most recent timestamps, those final few nodes will have the most write queries and read queries. And load will not be evenly distributed. Secondly, if you do want to change the partition boundaries, say if you want to switch the number of months per partition, as we have in this example, requires rebalancing the keys around it, so it's a little bit of a headache. And then finally, this is not good for partition keys which have a high cardinality. So if there's a large number of unique values, you're going to have so many partitions. So the next type of partitioning that addresses some of the pitfalls of range partitioning is called hash partitioning. In hash partitioning, we take the key, assign a hash function to it, mod it by the number of total nodes in our set, and then that assigns it to the particular node that the data lives on. MD5 is a common hash function used for this purpose. You take the MD5 hash of the key, turn that into an integer, mod it by the total number of nodes, and you end up with the node that the piece of data is supposed to live on. So this approach is better than range partitioning for data that has a high number of unique values. We're able to take the key and assign it to one of n partitions. Because the hash function is random, this also ensures that we have an even distribution of data. And we don't really need the extra effort of managing the partition ranges. Now, the downfalls of this hash partitioning is that we don't have the nice ability to do range queries because the data is not in any sorted fashion within the node. Also, it's more difficult to add and remove partitions. If we want to add and remove partitions and the number of nodes changes, we have to rehash all the keys. In a system that is highly scalable, it's common that we're going to have to add nodes. And rehashing all the keys is not realistic, and this is where our next partitioning strategy comes into play. So consistent hashing is the next partitioning strategy that we use, and it's beneficial because it removes some of the pain of rehashing all the keys when we want to add or remove a node. First, we take a server and we identify it by an ID. We then apply a hash function to this ID and assign it a certain position on a ring. And each key or data item is also hashed and is placed on this ring as well. So the key is stored in the next server clockwise from its calculated hash position. So this is better than hash partitioning. It reduces the amount of keys that we need to rehash when we want to add or remove a node. So say we want to remove a node, then all the keys that were once on that node are now directed to the node clockwise of that old node. And if we want to add a node, then we just need to rehash the keys that are in the adjacent servers. So with this approach, we still have the risk of hotspots. And this is where the concept of virtual nodes come into play. So now with virtual nodes, instead of each node having a single spot on this ring, so now the node is broken up virtually and arranged around the ring in multiple positions. And these positions are also created by applying a hash function multiple times to different nodes with different identifiers. So if you take a look at this example, you'll see the concept of virtual nodes. Each node now has 3 virtual nodes, assigned at different places around the ring. Okay, so now for the pros and cons. The pros of consistent hashing with virtual nodes is that we decrease the likelihood of hotspots, and we make adding or removing nodes a lot easier. So this is good for distributed databases that we presume to have unpredictable growth. Now the cons are that it's more complex to implement, although there are databases that implement this natively, Cassandra being one of them. And then also the lookup time for finding the key on the correct node has an extra step. You have to first find its hash position, and then find the next node on the ring clockwise to it. Okay, so the next type of partitioning that we have is called list partitioning. It's very different from hash partitioning and kind of similar to range partitioning in that the data is organized logically. So when it comes to list partitioning, the data within each partition matches a certain value or a certain set of values. So in the example here, you can see that the partitions are divided by region. We have one for Asia, North America, South America. So the data from each node falls into distinct, non-overlapping groups. One being the data is organized into distinct groups, as I said, so it makes the space in which we want to do queries a lot smaller. So queries in turn become more efficient. Secondly, it's easier to manage partitions because none of the data in each partition is related in any way. They're all isolated. So updating one partition shouldn't affect the other. And finally, this is really helpful in the scenario in which we need to have data located in different regions for regulatory compliance. So there's different data laws that govern where you can store data for security purposes and privacy purposes, and this will be a great strategy for that. Now the con is that there is a likelihood of hotspots because the data is not evenly distributed, and it's not super easy to redistribute it in a way that makes sense because the boundaries between this data are so distinct. And then finally, it's not possible to scale dynamically. If you want to have a new category, you have to go and manually create that partition. Now, what if you have data that has a certain access pattern that doesn't really allow you to take any of these approaches without having a hotspot? And this is where composite partitioning comes into play. So let's say we have an application like WhatsApp where we have a user, we need to get all the messages for a certain user within a certain time frame. We first need to get all the messages for a single user, which who knows how many that could be depending on how often the user uses WhatsApp. And then we need those messages to be ordered. Having a composite partition, say a hash partition for each user, and also a range partition so those keys are ordered would help with the efficiency of our queries. So this is just an example of how you can combine these partitioning strategies in order to optimize for your specific access pattern. All right, guys, that's a wrap for this video. I hope you enjoyed it. I hope it was helpful. Remember, I put out a new video every week. If these videos are helpful, please comment, like, and subscribe, and I'll catch you next time.